Another thing we can do with KSP values is use them to compare solubilities. And actually, the higher the KSP value, the greater the solubility. The only caveat is that the compounds that you are comparing have to have the same total number of ions in their formula. What does that mean? If I have MgCO3, which only has 2 ions in its formulas, magnesium 2 plus, and the polyatomic ion CO3 2 minus, I can't compare the KSP value of this formula with the KSP value of BAF2, which has 2 ions of F minus and 1 ion of barium 2 plus. So because this has 2 total ions and this has 3 total ions, I will not be able to compare KSP values. But if I look at MgCO3 and PbSO4, they both only have 2 ions total in their formula. So I can compare KSP values, and whichever one has the higher KSP value is going to have the higher solubility. So MgCO3 has a KSP of 3.5 times 10 to the negative 8, and PbSO4 has a KSP of 1.6 times 10 to the negative 8. Therefore, 3.5 times 10 to the negative 8 is the larger number, and so MgCO3 is going to have the higher solubility. When we look at their solubility values of 1.9 times 10 to the negative 4 versus 1.3 times 10 to the negative 4, we do see, in fact, that the higher KSP does have the higher solubility. In addition, using Le Chatelier's principle, we know that adding a common ion will shift the equilibrium, right? And this shift in equilibrium can therefore affect the solubility. How do we know that? Well, we're looking at our KSP expressions. We're in equilibrium here. And of course, the solubility or the molar solubility is going to be directly related to the concentrations of these aqueous ions. And so if we add a common ion, then that can directly affect the solubility of these slightly soluble ionic compounds. So let's go ahead and see an example here. So this is a saturated solution of lead 2 chromate, which of course is going to dissolve into Pb2 plus ions and CrO4 2 minus ions. When we add a common ion, we're going to see the effects which show the results here. So a common ion is added with a solution of Na2CrO4 is going to dissolve. And so when it dissolves, it's going to dissociate into 2 Na plus ions and then an ion of CrO4 2 minus. It's the CrO4 2 minus that's going to be added to our lead 2 chromate solution. And as you can see, it's a common ion, just like the ion we see here of chromate as well. So what happens when we add a common ion? It's simply saying that we're going to increase the concentration of the chromate ion here. And so because we have a lot more of the chromate ion, we're going to have to use up our lead 2 ions so that we can form our solid and, of course, push our equilibrium to the left. And if we're pushing our equilibrium to the left, we should be forming more solids. And that's why you see more solids forming up here in this overall test tube. So again, by adding more chromate ion here, I'm decreasing my lead 2 plus concentration. And if I'm decreasing my lead 2 plus concentration, I know that that's one of my concentrations that's related to what? My molar solubility. Now, I'm not going to be focusing my molar solubility on something that's the common ion, so this is not going to be the one I focus on. I focus on my lead 2 plus. And so what I know is if this is decreasing, therefore my solubility is also going to decrease. And so when you have a common ion that's going to shift the equilibrium to the left, you will see a decrease in your solubility. We can even go further and complete a calculation to reflect a common ion being added to the dissolution equation in the Avengers compound. So I'll see you there. So in our previous example, we calculated the solubility of calcium hydroxide in water. And we got as an X value of X is equal to 1.2 times 10 to the negative 2 molar, which represented our molar solubility. Now, we just said that the effect of a common ion is that it's going to shift the equilibrium to the left and decrease the solubility. So we are going to be proving that with this example. It says, what is the solubility in 0.10 molar CaNO3 That means we're adding a Ca2 plus ion and then 2 NO3 minus ions. So our common ion here is going to be Ca2 plus because our ions here are Ca2 plus and 2OH minus. So the one that's common between the two is going to be the calcium 2 plus. They also give us the KSP, just like they did before, of 6.5 times 10 to the negative 6. So just like before, if they give us the KSP value, we have to go ahead and get an equation for the dissolution of calcium hydroxide. And of course, we want to make sure that we're building a what? rice table so that we can show that our new calcium amount or our initial amount for our product of calcium is no longer going to be 0. It's now going to be 0.10 molar because we're adding in this common ion. So I set up my rice table. I have my dissolution equation. Calcium hydroxide is going to be in equilibrium to slightly dissolve into calcium 2 plus and 2OH minus. Everything is balanced. Now for initial, we know that our solids are not going to be used. They're pure. But for our calcium 2 plus, because it's a common ion, instead of it being 0 for the products, we're adding this in. So we're going to start with a 0.10 molar, which is given. Okay. And then OH minus is simply going to be 0. Now for the change, it's still going to be plus X here and plus 2X here. And so equilibrium is going to be 0.10 molar plus X and then 2X. Now they gave us a KSP value of 6.5 times 10 to the negative 6. So of course we can make an assumption here and we can get rid of X. That means that we're just going to have a KSP expression of Ca2 plus multiplied by OH minus, of course, squared is equal to the KSP value of 6.5 times 10 to the negative 6. So I'll go ahead and fill out my KSP expression. I'm starting with my KSP value, 6.5 times 10 to the negative 6 is equal to 0.10 molar multiplied by 2x raised to the power of 2. I'm going to divide by 0.10. That's going to cancel. I divide over here by 0.10. I'm left with 2x squared on this side. And then now when I divide these two numbers, I get 6.5 times 10 to the negative 5. What is 2x squared? It's simply going to be 4x squared, okay? Because it's going to be squaring 2 and then squaring x. That's why I got 4x squared. I'm going to have 4x squared is equal to 6.5 times 10 to the negative 5. To isolate x squared, I'm going to divide by 4 on both sides. When I divide this number, 6.5 times 10 to the negative 5 divided by 4, I get 1.625 times 10 to the negative 5. Once I take the square root of both sides, I get x is equal to 4.0 times 10 to the negative 3 molar, which is my new solubility. Now, previously, our molar solubility is 1.2 times 10 to the negative 2. So as you can see, it did decrease. So that common ion did cause a decrease in our overall molar solubility, just by using our previous example and this one here. And don't forget, folks, you always can go further and check any of your assumptions. So for example, I would take my 4.0 times 10 to the negative 3 and divide it by the initial amount given. And as long as it's less than 5%, I know that the assumptions that I'm making are still going to be good. All those equilibrium assumptions that you make or to verify, you still can use with these calculations here. All right, on to the next concept.